If you ask an AI to rename 1,000 financial files, it can effortlessly write the Python script to do it. But writing the code to describe the work and actually renaming the files are two different things. A system crosses the threshold into true agency only when it can access a secure digital environment, execute that script, and verify that the file names actually changed on the disk. Conflating the ability to reason with the ability to act creates a gap in our systems. It allows a machine to sound highly competent, while the actual state of the software remains completely unchanged. You've likely seen demos of agents attempting to use a computer by looking at screenshots and moving a cursor. But when a layout shifts or a pop-up resizes, the agent ends up clicking empty space, missing the target completely. To a machine, a visual interface is a matrix of colored pixels. If a background color changes or a button moves by an inch, the translation layer breaks. The AI loses its bearings because its environment is no longer where it expected it to be. Even relying on the underlying web code, the DOM, is brittle. If a developer renames a single CSS tag, the target effectively vanishes for the machine, causing the entire task to fail. When we evaluate these systems based on end task vibes, simply checking if the final output looks confident, we ignore these underlying failures. Digital labor requires mathematical certainty, not visual approximations. The stability of an agent depends on its position on the action representation ladder, a hierarchy that moves from the ambiguity of human language to the precision of machine-readable code. Plain text and visual interfaces occupy the bottom rung. Because they are unstructured and lack a standard format, they are nearly impossible for a machine to verify systematically. The middle tier consists of code execution and SQL databases. These offer binary certainty. A task either compiles and returns data, or it throws a measurable error. Typed APIs sit at the top. They provide rigid schemas and predictable contracts that allow different systems to communicate without the risk of misinterpretation. Building reliable agents requires pushing workflows as high up this ladder as the environment allows, moving away from visual interfaces in favor of structured data. We often discuss tool use as a single capability. In reality, it is a sequence of 5 distinct mechanical steps, and the failure of any one of them halts the entire process. First, the model must detect the need for a tool and pause its internal generation. Then it has to scan a catalog and select the specific tool required for the task. The most common point of failure is argument filling. If the AI produces a slight formatting error in the parameters, like a 3-letter airport code where the system expects a full city name, the input is rejected and the sequence crashes. If the arguments are correct, the system must then safely execute the action and integrate the resulting raw data back into the AI's reasoning loop. Because these nodes are linked, an error at step 2 or step 4 results in the same outcome: total operational collapse. Making these actions work in production requires a dedicated execution layer. This layer ensures all actions run in sandboxed, least privilege environments to prevent a single logic error from executing unintended commands on the main system. And then there is the observation layer. If a tool fails and returns a 5,000-line raw JSON error, feeding that directly back into the AI creates context pollution, overwhelming its ability to reason. The observation layer filters this chaos, translating a raw data dump into a clean, typed summary that keeps the AI focused on the next logical step. When failures occur, the recovery layer takes over. A conversational apology from the AI is useless for automation. The system needs a structured state that identifies the error type, the retry count, and the specific failure code. By generating machine-readable error states, an agent can identify why a task failed and mathematically chart a path toward a successful retry. Even as the reasoning capabilities of large language models continue to advance, they hit a ceiling that has nothing to do with their underlying intelligence. The true barrier is the environment itself, the messy, unstructured, organically grown internet we have built for ourselves over the last 40 years. Humans thrive in visual ambiguity. We can interpret shifting layouts and missing labels with ease. But mathematical machines require the opposite: strict, uncompromising structure. As long as we require machines to navigate interfaces designed for human eyes, the utility of digital agents will remain constrained by the environment. Operating a digital workforce at scale will require a shift in how we build software environments. This points toward a parallel internet, an architecture of APIs and strict schemas meant for machine verification, bypassing the human interface entirely. Chapter 8 of Rooted Layers provides the action surfaces and performance metrics used to build these autonomous software workers. It serves as a structural reference for engineers moving toward verifiable, agentic systems.